Today we're going to do sections 11.3 and 11.4, but we're going to switch the order and start with 11.4. We're going to be talking about areas of regular polygons and areas of circles. First, we're going to start with the regular polygon. I need to define some parts of regular polygons before we can look at the area formula for a regular polygon. Remember that a regular polygon has all sides and all angles congruent to each other. If I inscribe a regular polygon in a circle, they share the same center. The center of the polygon and the center of the circle are the same point, in this case point P. So the radius of the circle that goes from the center to a point on the circle is also the radius of the polygon. It goes from the center to the vertex, which is the point that is on the circle of the inscribed polygon. So this red segment here, AP, is a radius of the polygon, just like it's a radius of the circle. The apothem goes from the center and is perpendicular to a side. It also intersects the midpoint. So that altitude of this triangle right here made by two radii and the side is also a median because this is an isosceles triangle. So again, the apothem goes from the center of the polygon, is perpendicular to a side, and also bisects that side. So segment PF is the apothem. A central angle is made by two radii. AP and PB together make a central angle. There are the same number of central angles in a regular polygon as there are sides. So in this regular pentagon here, there would be 5 central angles. Because all the central angles together add up to 360, because they would also be central angles of these circles, and every central angle is congruent, I can figure out the measure of a central angle in a regular polygon by taking 360 and dividing it by the number of sides. Alright, now you're ready to explore the area formula for a regular polygon. Use these pictures to help you with these questions. Questions 1, 2, and 4 should have 3 answers, 1 answer for each polygon. For example, when it says how many sides does the polygon have, give me 1 answer for the triangle, 1 for the square, and 1 for the regular hexagon. Do that for numbers 1, 2, and 4. The other ones, numbers 3, 5, and 6, just have 1 answer. Okay, hopefully you were able to come up with the area formula for all regular polygons. But I want to talk about a special relationship in these 3 regular polygons: the equilateral triangle, the square, and the regular hexagon. Remember that these are half of a central angle, these angles made by the apothem and the radius. A central angle is made by 2 radii, and the apothem cuts that central angle in half. In a triangle, there are 3 central angles. So if I take 360 divided by 3, I get 120. So the central angle in an equilateral triangle is 120. And if I divide that by 2, I get 60. So this half central angle right here is 60 degrees. Also, the interior angle of equilateral triangles are 60 degrees, and the radius cuts that in half. So this angle is going to be half of 60, or a 30-degree angle. Hopefully you recognize our special right triangle here, a 30, 60, 90 triangle, where this side is the short side. So the apothem is the short side. Half the side of the triangle is the long side, or the short side times the square root of 3, and the radius is the hypotenuse, or the apothem times 2. In the square, we end up with a 45, 45, 90-degree triangle, or an isosceles right triangle. That means that half the side of the square and the apothem are equal. That's a nice relationship because anytime we know the side of the square, we can just divide by 2 to get the length of the apothem. Remember, that relationship only occurs in a square and no other regular polygon. And the radius is equal to those lengths times the square root of 2. Finally, we have the hexagon. The central angle of a hexagon is 360 divided by 6, or 60, and the angle made by the radius and the apothem is half of that, or 30 degrees. Also, the interior angle of a regular hexagon is 120 degrees, so this angle made by the radius and the side is half of that, or 60 degrees. So once again, we have a 30, 60, 90 triangle, but now the angles have switched. So now half the side of the hexagon is the short side, and the radius, the hypotenuse, is twice that length. The apothem is the long side, and is this blue length times the square root of 3. So anytime you're finding the area of an equilateral triangle, a square, or a regular hexagon, you will be asked to use these special right triangles instead of trigonometry to solve for the missing parts. That means you'll have to give your exam answers in exact form with square root answers. Alright, now we're going to move on to circles. You're going to do an activity using what we just figured out about areas of regular polygons. Hopefully you found out that if you take 1/2 the length of the apothem times the perimeter of the regular polygon, you get the area of that regular polygon. We're going to take that idea and the idea that if I have a regular polygon and I keep increasing the number of sides, I get closer and closer to a circle. So if I calculate the area of a regular polygon with many sides, that area is going to be very close to the area of a circle. So you're going to calculate the areas of these different regular polygons here. Now most of the hard work has been done for you. We can use the number of sides to figure out the perimeter of that regular polygon. In each of these cases, we're given that r is the radius. We're going to keep that as r and not plug in any numbers there. So a side is going to be 1.73 r. So the perimeter of that regular polygon is going to be the number of sides times the side length, or this number times r. Then we have to multiply by the apothem, which is, in this case, this number times r. Finally, we'll put that all together to get the area plus the 1/2. So we'll do 1/2 the number of sides times the side length times the apothem and put that answer here. Remember that r times r is r squared. Go ahead and calculate the areas of all of these polygons here with these different numbers of sides. You should notice something about the number in front of the r squared that you get when you get to here. Another demonstration about the area of a circle that we're going to do right here. If I take the circle and cut it into equal sectors like this, and I move them around and put them together, I get a shape that's like a parallelogram, where the height is the radius and the base is half the circumference. So if I multiply base times height, I get pi r squared. This is the area formula for a circle. Finally, we're going to look at the area of a sector. Anytime you cut out a piece of a circle, for example, a piece of pizza, we call that a sector. Do you remember when we came up with a proportion for finding the length of an arc? And we used a ratio of degrees with the central angle and the whole circle, and a ratio of lengths with the arc and the whole circle, the circumference. Now, instead of doing a ratio of degrees and a ratio of lengths, we're going to look at a ratio of degrees and a ratio of areas. So over here, we're going to do a ratio of degrees. So on top, we have the central angle, and then on bottom, we have the degrees of the circle, which are always going to be 360. Then we have our ratio of areas. So on top, we're going to have our area of our sector, and on bottom, we'll have our area of our circle, which remember is pi r squared. And once again, I can use cross multiplication to solve this proportion. So if I know any two of these three values, I can find the third one by cross multiplying and solving. So once again, this proportion is going to be much easier to understand and much more useful than this formula here. So know this proportion by remembering this ratio of degrees and this ratio of areas.